Hello and welcome to the last video lecture of chemical kinetics for this course. And today we are going to talk about heterogeneous catalysis. So you have already studied homogeneous catalysis, where both the catalyst and the substrate were in the same phase, basically the solution phase. So in this section, we would deal with a solid gas interface. So the catalyst would be the solid form and the substrate would be in the gaseous form. So just like the enzyme catalysis, the gas would interact with the solid to make a solid gas intermediate. So this could be the substrate catalyst, just like the enzyme substrate complex. This would be an intermediate where the gas molecules would be attached with the solid interface. And then at the next step there will be the reaction. So we get the product as a gaseous form, obviously, and the catalyst would be available again to take some fresh substrate for the reaction. Okay, so now we will discuss the above steps in a somewhat little bit more detail. Okay, so here we start with that. So the image here at the left, so this is the solid surface that I have demarked here. When a solid substance reacts with a gas, basically the reaction happens at the surface. Okay, so this is the gas molecule, so I can draw them like this. So the very first step, obviously, the gas molecule will have to diffuse towards the surface. Okay, and then in the next step, the gas molecules would be sitting on the top of the solid surface. So, but here at this point, we would refer them as not just like the gas molecule, not as the gas molecule, but we call them adsorbed molecules on the solid surface. Okay, so here you see the the molecules here are not as free as they would have been in the gaseous state. Okay, so they have some degrees of limitation in regarding movement and all. And then in the next step, there will be the chemical reaction between the two between the two adsorbed molecules. So we can then draw something like this, a picture. Okay, so this is how the chemical reaction happened over here, and we can call it as the product P, because after reaction the product is supposed to be formed, so we can call it the product P. And then at the last step, this product has to go away from the surface. So the product P supposed to be removed from the surface, so that now the surface is free to take fresh gas molecules. So these four basic steps are classified as something like this. So the first step, this is called diffusion, because gas molecules are diffusing towards the solid surface. So the step one is called the diffusion. And the next step, where the gas molecules are sitting on the solid surface, okay, so almost in an immovable manner. So this step we call adsorption. Okay, so remember, this is not absorption, so there is a basic difference between adsorption and absorption. So anyway, this is called the adsorption, and these molecules are called adsorbed molecule. Okay, and so the next step, this step is called the chemical reaction, where the two gas molecules react. So I can actually also number them. One is the diffusion, second is the adsorption, third is the reaction. Okay, and then at the last step, where after formation of product, the product goes away from the surface. So this is exactly the opposite of the adsorption. So we can call this process as desorption. Okay, desorption, and this desorption process is also coupled with the diffusion back to the environment. Okay, so this happens together with again some diffusion, but we don't consider that as a separate step. So together we call it here as a desorption step. So these are the four basic mechanistic steps for a solid gas solid and gas interface based heterogeneous reaction. So now we'll take a real life example in order to show you how these few steps proceed. So what we are going to do, we are going to follow a surface which is the hydrogenation of ethylene on nickel surface. So this is nickel, okay, and the reaction we are going to talk about is the this is ethylene, okay, and when hydrogenation process occurs, it forms ethane gas, and it happens on solid nickel surface. So the procedure is actually follows exactly like that. So first of all, we have the hydrogen gas molecule. It would be diffusing in near to the solid surface, and the next step is the hydrogen molecule would be sitting on the solid surface, behaving as an adsorbed molecule. Okay, so this we call hydrogen adsorbed on the nickel surface. And then further, what will happen that now the ethylene molecule would come near the adsorbed hydrogen molecule. So therefore, so this is so first, once again, this is diffusion, and this step is called adsorption. And after adsorption, we have the reaction step. So what happens is we have the hydrogen molecule sitting on the solid surface, and we have another substrate, that is the ethylene, would be interacting with the hydrogen, the adsorbed hydrogen molecule. And as a result, the chemical conversion would happen. So that means now we have this ethane molecule. Okay, so here I have drawn an extra step here. So together, this and this, we can think about that this is the chemical reaction step where the ethylene molecule is actually reacting with the adsorbed hydrogen molecule. So now that the product is formed, so in the last step, that is in the desorption step, we would see that the ethane gas, okay, goes away from the surface and making the catalytic surface free or available for another fresh molecules of hydrogen and subsequently ethylene to react on. Okay, so this is a chemical reaction that takes place industrially. Okay, so and we need a special kind of nickel surface for this reaction to achieve, but we are not going into the details of that. Just remember, these heterogeneous reactions are very important industrially, and we will find some important examples later. So now, the entire heterogeneous catalysis, once again, as I told you, consists of four major steps: diffusion, adsorption, reaction, and desorption. All right, and so before we proceed, we want to ask ourselves a question: what is the role of the solid surface here? The role of the solid surface is exactly that we have described a few lectures ago when we talked about activation energy, Arrhenius equation, etc., or catalysis, that the solid surface provides an alternate route for this reaction having a lower activation energy barrier. So that means had the ethylene or hydrogen had to react each other, it would have gone through a very high activation energy barrier. So normally it is not possible. So that's why we needed a surface nickel. So at particular conditions also, but we are not mentioning that conditions here. So at that condition, the nickel surface is offering both the substrates an alternate pathway with some lower activation energy, so that at the given condition the reaction takes place. Okay, now once again coming back, so there are 4 major steps. Okay, so the question is, for any chemical reaction that goes in through a multiple steps, that we have learned in our first lecture, that there must be a rate determining step. So the question is, what is the rate determining step for this heterogeneous reaction? In other words, the rate determining step is actually the slowest step for any mechanism, alright, that is going through a multiple steps. So the question is, out of these 4, diffusion, adsorption, reaction and desorption, which is the slowest step or becoming the rate determining step? Well, the answer is, it is the adsorption process that is the slowest step, and that becomes the rate determining for the entire heterogeneous catalysis. So therefore, if we study the rate of adsorption or the kinetics of adsorption in the context of such reaction, then only we'll be able to study the mechanism or the kinetics of heterogeneous catalysis or heterogeneous reaction. So therefore, the process of adsorption is very important to us. Okay. So before we proceed further, I want to mention a few terminologies that whenever we have a solid surface, okay, so the solid surface is also called adsorbent, okay, and the gas molecule that is getting adsorbed, so after it got adsorbed, so that molecule is known as adsorbate. Okay, so these are some terminologies that we should be familiar of. So now the question is, we have to study little bit the process of adsorption. So any catalysis or any rate law, for example, we have rate is equal to some rate constant multiplied by some concentration term, isn't it? To the power n or whatever. So we are familiar of this kind of expression. Now the question is, the heterogeneous catalysis has to be expressed in terms of adsorption. So what we would now be looking at is how. So basically, the rate of, we can write the rate within bracket heterogeneous catalysis is equal to basically the rate of adsorption, and so the question is how the rate of adsorption is connected with the concentration of the substrate molecules, okay, something like that, or anything else. So that means how we can connect the rate of the heterogeneous catalysis or the process of adsorption with the concentration of the gas molecules or the availability of the adsorption sites, etc. Okay, so in the next few minutes we will be concentrating on establishing a relationship between the adsorption process with the concentration or the adsorption sites or the pressure of the gaseous substrate, etc. All right. So let's erase the board and let's try to find out a mathematical equation by which we can relate this phenomenon. Okay, so let's do that. So now we are going to learn about a theory that explains the adsorption of gas molecules on a solid surface. So this theory was introduced by Irving Langmuir in 1932. He was an American physical chemist. So he introduced a mechanistic model for adsorption of gases. So I have drawn the mechanistic model here by a schematic diagram. So you see, on a solid surface, I have demarcated with some bold black patches. So these are called adsorption sites. So in a solid surface, according to Langmuir, there are some specific and fixed number of adsorption sites exactly where the gas molecule would sit. That means the adsorption of gas molecule would take place. And in this model, Langmuir assumed few statements. Okay, so we would come across those assumptions one by one. So the first few major assumptions came from the thermodynamics itself. So we call it the thermodynamic consideration. So firstly, the entire adsorption process, as I mentioned, is a slow process, and it goes through an innumerable reversible steps. So it's not a single step process. So it's a reversible multi-step process. And then at each and every instant, the process goes via establishment of an equilibrium. So therefore, whenever the gas molecules are getting adsorbed, at the same time they are getting dissolved also. So it's a kind of a dynamic thing going on. And at every instant, whenever this adsorption and desorption process is going on, at every instant the process goes via formation of some instantaneous equilibrium at each and every step. So you can understand the process is obviously a slow one. And then further, Langmuir assumed some special things that are, number one, there are some fixed number of equivalent adsorption sites. Each sites are the same, equivalent. So there is no preference of the gas molecules to sit on a particular site. And then one of the very most important assumptions is one molecule sits on one adsorption site. So therefore, the adsorption is limited to monolayer only. Okay. So that means we won't have a gas molecule sitting on another gas molecule, but it would exactly sit on a solid surface. It would, so the adsorption at the best possible scenario is the formation of a complete monolayer. So no multi-layer formation is assumed in Langmuir's model. And then lastly, the adsorbed molecules, once they get adsorbed, well, they can be dissolved also, but once they adsorb, they don't roll over to their nearby sites, and also during the adsorption they don't interact with each other. Okay, so that was some of the major assumptions of the Langmuir's model. So without this assumption, we are unable to proceed to derive the mathematical equation that actually explains the extent of adsorption with respect to the pressure of the gas molecules. So I'm going to erase these assumptions, and now I try to derive the Langmuir's equation for adsorption of gas molecule on a solid surface. So while deriving, we start with the statement that at equilibrium, obviously there is equilibrium at any instant, the rate of adsorption is equal to the rate of desorption. That means the rate of forward reaction is equal to the rate of the backward reaction. So very well, So what is the rate of adsorption? So rate of adsorption, obviously we can relate with so this is some rate constant, so the rate constant of adsorption, some arbitrary constant, multiplied by we can think about on what factor. So you see, the more number of gas molecules are there, the adsorption will be more, because there will be more statistical probability for the gas molecules to come on the solid surface, and the adsorption will be quicker. So therefore, the concentration of the gas molecules, or in other words, the pressure of the gas molecule, we can think about. So here comes the kind of the concentration term, and then multiplied by, you see, the more the number of the vacant surfaces are there, that means the vacant position, the rate would be faster, isn't it? So therefore, we can multiply with, we can say that the percentage of vacant sites. So this means the percentage of vacant adsorption sites on the solid. So this is equal to rate constant of desorption, so another arbitrary constant, we call it K desorb, and then multiplied by, now it would only depend on what? It would only depend now on the number of molecules that are adsorbed. Okay? So because there are more number of adsorbed molecules, obviously the desorption rate will be higher. So then how can we express that? So obviously we can count the molecules that are adsorbed. So what we can express, that it is now actually the percentage of the occupied sites. Alright, so we can write multiplied by the percentage of occupied sites occupied by the adsorbed gas molecule. So now we can see an equation building up, but we would like to express the percentage of the occupied site. Okay, we can write it this way. The percentage of occupied sites, since percentage is actually synonymous of fraction, so we can represent this in terms of a fraction, and we call the fraction as theta. So we define theta as, that is, number of sites that are occupied by the adsorbed gas molecule divided by the total number of adsorption site available. Okay, so basically when you multiply that by 100, it becomes the percentage, but here instead of percentage value, we are expressing it in terms of theta, so that expression in this equation becomes simpler. So therefore, we can call it as equation 1. So the equation 1 then transform into, so we can write again the K adsorption multiplied by P multiplied by here. Now instead of percentage of vacant sites, so we have the fraction of vacant sites. So the fraction of vacant site will definitely be 1 minus theta, because whenever we talk about the fraction, so it means 100% means the value of 1, it should be representing the total occupancy. So is equal to K desorption, and then obviously multiplied by theta. Okay, so if I want to rearrange, that means if I want to express the value of theta, so what expression would we get? Okay, so let's erase this part and let's try to write the expression of theta on the board. So if we want to calculate the theta from this equation, so it would take up a form like this, K adsorption divided by K desorption multiplied by pressure P divided by 1 plus K adsorption divided by K desorption and multiplied by P. Alright, so here once again, as you can see, the K adsorption divided by K desorption and according to our understanding of equilibrium, this ratio becomes the K equilibrium constant of the adsorption process. So therefore, we can write the same equation as theta is equal to K equilibrium multiplied by pressure divided by 1 plus K equilibrium multiplied by pressure. So therefore, the same thing can be represented as some constant A multiplied by P divided by 1 plus AP, where A is a constant. So here I have simplified this expression because I have disregarded some other physical phenomenon. So therefore, this constant A is actually not exactly the K equilibrium, but it is associated with something else. But at this stage, we are not going into that detail. But anyway, the theta can be expressed as something like this: AP divided by 1 plus AP, where A is a constant. Okay. So according to our derivation here, the A is the K equilibrium, but actually it is a little bit different than K equilibrium, but let's ignore that. But this is a mathematical equation, and this is called the famous Langmuir's equation for adsorption of gas on solid surface. Okay. And the thing is, can we graphically plot this theta versus pressure? So, if we want to plot pressure P versus theta, so theta is plotted on the y-axis, P is in the x-axis. So these kind of plots are actually considered when the temperature T is constant. Because if the T is not constant, then we cannot talk about the pressure because it will vary continuously. So therefore, at constant temperature, the theta versus P data, these kind of graphs are called isotherms. Okay. So according to this equation, theta versus P, you see that if you look at the equation here, so at the lower value of P, that is when P is negligibly small, theta is proportional to P pressure. So therefore, at lower value, the theta would increase like this. And at very higher value of pressure, you see, the unity the 1 can be neglected with respect to AP, and then it cancels out, and then theta becomes independent of pressure. So therefore, at very high pressure, the theta value would be independent of pressure axis. So it becomes parallel to pressure axis. So this kind of graph plots is also known as Langmuir's isotherm, because this kind of graph plots according to is fitted according to this mathematical formula. So the question is, can you draw this theta versus P plot with different values of A? That means if we can draw A1 greater than A2 greater than A3. So can you draw that? So how would this graph would look like? Okay. So that's a little exercise. You can do it. But remember, this Langmuir's isotherm is a very famous type of adsorption isotherm, and historically it explained many different types of adsorption phenomena. Okay, so like many gases on activated charcoal, many liquids on silica gel, etc. So experimentally, those theta versus P plots, the best fit would take a shape like that, and Langmuir's isotherm, or like Langmuir's chemical equation, was first to explain this kind of graphical behavior. And due to this fundamental work and many more surface chemistry related work, Langmuir was awarded Nobel Prize later on. Anyway, so now let's see that we got a connection between theta and the pressure P. So let's try to find out how the rate of the heterogeneous reaction would be connected with the theta. So let's do that now. So we have already seen that in a case of heterogeneous reaction, the adsorption was the rate determining state. So therefore, the rate of heterogeneous reaction would now be proportional since the adsorption is a thermodynamically controlled one. So we don't talk about the rate of adsorption because it doesn't have any meaning. But you see, if there are more number of adsorbed gas molecules, obviously there will be faster reaction because before reaction you need the gas molecules to be adsorbed on the surface. So therefore the rate of heterogeneous reaction would be directly proportional to the theta. That means the fraction of gas molecules that are occupied on the surface or the fraction of adsorbed gas molecules. So therefore, since this is a proportionality relationship, so we can write the rate, okay, is equal to, we have some constant, we can call it Z, which is equivalent to the rate constant multiplied by theta. So therefore, since theta contains pressure, so here in the reaction, the only measurable parameter is the pressure P of the gas. So therefore, we can write the rate of the heterogeneous reaction is equal to minus dP dt. So why we call minus? Because when you measure the pressure here, so the pressure gets decreasing because you measured the pressure of the available gas molecules on the surrounding. So once the gas molecule starts to get absorbed, the pressure falls. So therefore, this is the negative sign. So minus dP dt is equal to Z AP divided by 1 plus AP. All right. So this would be our generalized rate equation for heterogeneous reaction. Now you see this rate equation is very simple, okay, and it follows the basic principle of adsorption, which is for this context, this kinetics is based on the Langmuir's theory or Langmuir's adsorption equation. So right now we are going to consider three cases, okay? Three cases of what? So the three cases that we are going to talk, that in one case only one type of gas molecules, okay, getting adsorbed and forming the product. And in another situation, two different types of gas molecules getting adsorbed simultaneously. And in the third process, one gas molecule is getting adsorbed and another gas molecules, coming from top, they just get collided with the gas molecule sitting on the surface and the product is formed. So let's consider the three cases one by one and let's find out the kinetics in each case. So first we talk about the situation 1 where a single gas gets adsorbed to form a product, and we have seen this mechanistic model at the very beginning of this lecture. This is one single kind of gas molecule is getting adsorbed. So the entire process goes through 4 steps, but the rate determining step is adsorption, and therefore the rate is equal to given by this expression that we have already seen. So now there are 3 different cases possible. In one case, we think about one extreme when at very extremely low pressure the product AP becomes negligible with respect to 1. So then therefore the rate becomes is equal to equivalent to ZAP. So therefore this is nothing but the first order kinetics. Okay, and when in the other extreme end, when the pressure is very high, so the AP becomes very high with respect to 1, so we can neglect 1 with respect to AP. So therefore the kinetics follows a 0 order rate law. All right, and in between, when P is intermediate, that means when P is neither very high or not very low, the order is between 0, so it should be greater than 0 but less than 1. So we can call it, we can expect that the order would be a fractional one. Okay, so it's a fractional order kinetics we can think about. So an example where we actually find these situations happening, it is the, we can write the decomposition of phosphine gas on the tungsten surface. So at very low pressure of phosphine, the kinetics follows a first order rate law, and at very high pressure it follows a zero order rate law. So this situation is comparatively simpler, as apparent from this simple expression of the heterogeneous rate law. And therefore we come to the situation 2, where two different types of gas molecules are getting absorbed. So I'm going to describe this here. So in the second situation, two different gas molecules are simultaneously getting absorbed in the adjacent sites. So what it happens now, that we would encounter two different types of theta. That means the fraction of occupancy. So the fraction covered by gas A is given by theta A, and the other one for theta B. So therefore the fraction stays vacant at any time is equal to 1 minus theta A minus theta B. So basically the total occupancy becomes theta A plus theta B, and hence the vacant occupancy goes like this. And obviously the rate becomes minus dPdt is equal to, now it would look like some kind of a second order reaction, Z theta A multiplied by theta B. So our job is to find the two unknowns, theta A and theta B. And obviously to find two unknowns, we need two simultaneous equations. So therefore, we try to form the equations right from the beginning. That means from the consideration of equilibrium, where the rate of adsorption equals to the rate of desorption. So for case of gas A, we have this equation, and we can call it the equation 1. And for the other one, we have this, and we call the equation as 2. So from here, we have to find out theta A and theta B. So obviously, if we divide the equation 2, or rather, if we divide equation 1 by equation 2, so therefore, that would give us the ratio theta A divided by theta B is equal to something like this. So Ka Pa divided by Kb Pb multiplied by Kb prime divided by Ka prime. So it's needless to say that this prime, Ka prime and Kb prime defines the desorption constant for desorption, and Kb defines as the constant for adsorption. So therefore, so from this we can find the value of theta A. So we can express the value of theta A by this. So here if we look at that, Ka divided by Kb, so this part becomes the equilibrium constant. Okay, K equilibrium, not this one, Ka divided by Ka prime. So yes, so Ka divided by Ka prime, this becomes the K equilibrium of A, so we call it Ka. And then we have Kb prime over Kb, so this becomes inverse of K equilibrium for gas B, alright? And then we have Pa divided by Pb and multiplied by theta B. So here we have now got an expression of theta A in terms of theta B, isn't it? So if we now substitute the value of theta A with this one here, and then if we solve for theta B, we get the expression for enter theta A and theta B. So therefore, if we do that, then finally what we should be able to come is a value like this. So theta A would become theta A is equal to K equilibrium A Pa divided by 1 plus Ka Pa plus Kb Pb. Okay, so that's going to be theta A, and if we do the same thing, the theta B would be coming something like this, Kb Pb divided by 1 plus Ka Pa plus Kb Pb. So remember, these K's are equilibrium constant. So therefore, from this we can readily write the equation for minus dp dt, that is the rate of the heterogeneous equation, that is z theta a multiplied by theta b. So let's clean the board and write freshly the total expression of this, where theta a and theta b are something like this. So if we put the values of theta a and theta b in previous case, we get the rate of the reaction minus dp dt is equal to something like this. So we have a square term at the denominator, and numerator we have rate constant multiplied by the equilibrium constants multiplied by Pa and Pb. So this mechanism is known as Langmuir Hinshelwood mechanism, and also this rate equation is called the Langmuir Hinshelwood rate equation. So one of the general example is that we can talk about. This is a very common phenomenon that actually occurs in many automobiles exhaust, that the formation of carbon monoxide gas due to incomplete combustion of fuel is actually turned into a less harmful carbon dioxide through aerial oxidation, and a solid state catalyst actually converts this carbon monoxide to carbon dioxide. And so this follows the Langmuir Hinshelwood rate equation, and this reaction takes place at the catalytic converter of the automobile's emission, automobile's gas exhaust chamber. And another special case we can think about, that if there is a possibility that both KAPA is actually and KBPB could be much less than 1, both cases. That means it is possible at very extremely low pressure of PA and PB, so both these two terms becomes negligible with respect to 1, then the minus dp dt, the rate law, you can see that it will become a second order, it will follow a second order rate law, or a second order kinetics. So the examples of this special case is the hydrogenation of ethylene C2H4 on copper surface, solid copper surface. Okay. So now we are left with the third situation. Okay. So let's clean the board and talk about the third situation, where one gas molecule is already adsorbed and another gas molecule collides with the adsorbed one. Okay, so let's take a look. So here, in the last situation, what we can think about, that already there is a gas molecule B adsorbed on the solid surface, and another molecule A just collides with it. So it is a collision step here. And then after collision, the reaction takes place and the product goes away. So the most important feature is, you see, the gas molecule A, so this is not adsorbed, so this is never adsorbed on the surface, so it just collides on B. So therefore, the rate definitely would be proportional to the fraction of the gas molecules occupied, that is, theta B. So the rate is proportional to the fraction of the gas molecules B getting occupied, that is theta B. And also, we can say the rate is proportional to the pressure of the gas A, isn't it? So more the pressure of A, the more would be the collision, and the more would be the reaction. So if we combine all the two, then we can write that rate is equal to minus dp dt is equal to Z multiplied by the pressure PA and multiplied by theta B. Okay, so therefore, we can also write it here Z PA, and we have, if we think about APB, divided by 1 plus APB. Okay, and so therefore we take this A as a constant inside here, so we can write it as Z prime multiplied by PA PB divided by 1 plus A B. So also again we have a simpler rate law. Okay, and this particular reaction mechanism or the particular rate law is called Eley-Rideal mechanism. So the previous one was Langmuir Hinshelwood mechanism, and this one is Eley-Rideal mechanism. So in this Eley-Rideal mechanism, obviously, that you can say that a different situation would appear. So if we conduct the reaction with a very low pressure of PB, alright, so you can see that equation can be second order, and if we conduct the reaction with a very high pressure of PB, the reaction can be of the first order. Okay, so an example. So I think you have seen the examples before at the beginning of this lecture. That is the hydrogenation of ethylene on nickel surface. Okay, so if we remember the mechanism, so this one was our hydrogen B gas absorbed on the surface, and the molecules get colliding is the ethylene. Okay, and so therefore the reaction happened, and we had the active catalysis. So remember, so these are the three major types of the solid gas heterogeneous catalysis, and this heterogeneous catalysis is one of the most important chemical transformation that takes place industrially, and I would recommend to follow the Atkins textbook to find out some specific applications of this solid gas heterogeneous catalysis that are very relevant to our daily life and also for the industrial application. Alright, so this was all about heterogeneous catalysis and all about the chemical kinetics as a required course curriculum for the first year undergraduate chemistry course. So there will be one more tutorial I will share with you, and the solutions would also be shared with you later. So I hope that you have followed and enjoyed the video lectures. So they would be available to you all the time. So I recommend you to watch all the lectures and study all the materials that are being shared with you, and you can reach me anytime with any questions, and I wish you all the best in your study, and I will see you later when you come back to the campus. So till then, goodbye.